the concept of equilibrium. Now let's say we have a reaction. A plus B will give us C plus D. Here A and B are known as the reactants and C and D, they are the products. After a specific time period, if A and B are absent in the reaction mixture, it is known as an irreversible reaction. If A and B are present along with C and D in the reaction mixture, it is known as a reversible reaction, or we call it an equilibrium reaction. An equilibrium reaction can be expressed as follows. A plus B will give us C plus D, and this arrow will depict that the reaction is reversible. Now if we plot the graph between the reaction rate versus time for an equilibrium reaction, we can see that initially the rates are different for the forward reaction and the backward reaction, but after equilibrium will take place at, let's say the time is t is equal to t naught. Then after time t naught, this reaction will undergo equilibrium. So at equilibrium, we can say that RF, or the rate of the forward reaction, will be equal to the rate of the backward reaction. So we should remember this. Now let's talk about the equilibrium law. The equilibrium law states that the product of the concentrations of the products when divided by the product of concentrations of the reactants is equal to a constant, which is known as the equilibrium constant Kc. That is, now let's say we have a reaction. A plus B will give us C plus D. So Kc is the product of concentrations of the products. So C times D concentration divided by the product of concentrations of the reactants. So that is A times B. So this is a constant. It is known as the equilibrium constant. And it is known as Kc because C will represent concentration. Next point, the value of the equilibrium constant depends on the reaction and also the temperature at which this equilibrium will take place. For an example, let's say we have two reactions. One is AB, it gives us C plus D, and this will take place at 300 Kelvin temperature. And also we have another reaction which takes place at 400 Kelvin, the same reaction. So if this is Kc1 and if this is Kc2, Kc1 is not equal to Kc2 because the temperature is different. So if we have the reaction A plus B will give us C plus D at 300 Kelvin, and also at 300 Kelvin we have another reaction. P plus Q will give us R plus S. So even though the temperatures are the same, these two are two different reactions. So here you have A plus B will give us C plus D, and here you have P plus Q that will give us R plus S. So since these two are separate reactions, this is Kc3 and this is Kc4. Kc3 is not equal to Kc4. Depending on the value of the equilibrium constant, we can compare the amount of reactants and amount of products present in the medium at equilibrium. For an example, let's say if the equilibrium constant is greater than a value of 10 to the power 6, then we can say that the amount of products is greater than the amount of reactants. Therefore, this reaction is almost at completion. If the Kc value is equal to 1, then the amount of products is equal to the amount of reactants. And if the Kc value is less than the value like 10 to the power minus 3, we can say that the amount of products is less than the amount of reactants. Therefore, there's no visible reaction taking place because this value is very small. Now, let's talk about the equilibrium constant Kc. Here, let's consider an elementary reaction. And the temperature is T Kelvin. And the reaction is AA. Let's say it is a gas. And BB, it is also a gas. We have the equilibrium arrow. And C, D. These simple letters, they are the stoichiometric ratio. And if we write rate expressions for the forward reaction and the backward reaction, first of all, let's consider the forward reaction. If the rate is Rf, then the rate equation will be K, let's say the rate constant is K1, A gas to the power A, and B gas to the power B. If we consider the backward reaction, that is Rb, let's say the rate constant is K2, then C gas to the power C, and D gas to the power D. For an equilibrium reaction, Rf is equal to Rb. The rate of the forward reaction is equal to the rate of the backward reaction. So we get the equation Rf is equal to Rb, and if we substitute the values from the first and the second equations, we get K1 times A gas to the power A and B gas to the power B is equal to K2 times C gas to the power C and D gas to the power D. So now these are the products and these are the reactants. So according to the equilibrium law, it should be the ratio between the products and the reactants. So if we subject K1 over K2, we get C gas to the power C times D gas to the power D divided by A gas to the power A times B gas to the power B. So this will be equal to Kc. Therefore, finally, we can write the Kc expression C gas to the power C times D gas to the power D divided by A gas to the power A times B gas to the power B. So this is the equilibrium constant in terms of their concentrations. Now let's talk about the equilibrium constant Kp. So here, for reactions involving gases, it is more convenient to use the equilibrium constant or express the equilibrium constant in terms of partial pressure. So P in this case represents pressure. So let's take the equation AA gas plus BB gas will give us Cc gas and D of D gas, right? So according to the ideal gas equation, first of all, let's write assuming ideal behavior for these gases. We can use the ideal gas equation, which is PV equals nRT. So if we divide this equation by V, then P is equal to N over V RT. And also we know that concentration is equal to number of moles over volume. That is, C is equal to N over V. So instead of this, we can represent it in terms of concentration. So P will be equal to C times RT. Since this reaction takes place at a constant temperature and R is the universal gas constant, so RT is a constant. So if we take if you take the rate equation for the forward reaction, let's say it is RF, and K1 times A to the power gas concentration to the power simple A, concentration of B gas to the power simple B. So using this, we can write K1 times, this can be partial pressure of A gas divided by RT, the entire thing to the power simple A. Similarly for B, it is PB gas over RT to the power B. So if we further simplify this, RF is equal to K times RT to the power A plus B times partial pressure of A to the power simple A and partial pressure of B to the power simple B. So that is the first equation. Similarly, for the reverse reaction, you can say that RB is equal to K2 over RT times to the power C plus D, and PC, that is the partial pressure of C, to the power C times partial pressure of D to the power D. So that is the second equation. Since this is an equilibrium reaction, we can say that RF is equal to RB. Therefore, K1 over RT to the power AB and partial pressure of A gas to the power A times partial pressure of B gas to the power B is equal to partial pressure K2 over RT C plus D and partial pressure of C to the power simple C and partial pressure of D to the power simple D. So these are the products and these are the reactants. So if we subject K1 over K2 times RT, so this will be C plus D minus A plus B. We get PC gas to the power simple C and partial pressure of D to the power simple D divided by partial pressure of A to the power simple A and partial pressure of B to the power simple B. So according to the equilibrium law, this will be Kp. And finally, we have the equation Kp is equal to partial pressure of C to the power C and partial pressure of D to the power D over partial pressure of A to the power A times partial pressure of B to the power simple B. Now let's talk about the relationship between Kc and Kp. So if you write the Kp expression for this reaction, Kp is equal to partial pressure of C gas to the power C times partial pressure of D gas to the power simple D divided by partial pressure of A gas to the power simple A times partial pressure of B gas to the power simple B. So, assuming ideal gas behavior by the equation PV equals nRT, we can derive P is equal to CRT. So, PC is equal to concentration of C times RT. PD is equal to concentration of D times RT. Partial pressure of A is equal to concentration of A times RT. And the concentration, and the partial pressure of B is equal to concentration of B times RT. So if we substitute these values, we get Kp is equal to C to the power C times D to the power simple G divided by A concentration to the power A times B concentration to the power B. And RT will be C plus D minus A plus B. So if we put a substitution, let's say it is delta N. Delta N will be equal to C plus D minus A plus B. And instead of this part, which is the Kc expression for the above reaction, we can say that Kp is equal to Kc times RT whole thing to the power delta N. Now let's move on to a question. Write down the Kc and Kp expressions for the given chemical reactions. So if we start with the Kc expression, Kc is equal to O2 gas to the power 1 times H2 gas to the power 3 because the stoichiometric numbers are 2, 1 and 3, and divided by N3 concentration. Let's start by writing the Kc expression. So here the stoichiometric values will be 2:1:3. So Kc is equal to the concentration of nitrogen to the power 1 times concentration of hydrogen to the power 3 because the number is 3 divided by the concentration of ammonia gas to the power 2. And if we write the Kp expression, Kp is equal to partial pressure of nitrogen gas to the power 1 times partial pressure of hydrogen gas to the power 3 divided by the partial pressure of ammonia gas to the power 2. So if we move on to the next question, that is the part B. Okay, if we write the Kc expression, for solids, the concentration will remain constant. Therefore, we have to consider the concentration of CO2 gas only, that is 1. And the Kp expression, so we write the Kp expression for gaseous substances. So the partial pressure of carbon dioxide, power 1, and these two are solids, so we can just ignore them. Let's move on to the next question. 6.2 moles of HI was introduced into a closed system of volume 5 decimeter cube and heated to a temperature of 525 Kelvin. 30% of HI dissociated into H2 and I2 gases. Calculate the Kc value of the equilibrium at this temperature. First of all, we can write the balanced chemical equation. 2HI gas will give us H2 gas plus I2 gas. And they have given the initial the initial number of moles of HI. So let's write the initial amount, and that is 6.2. We don't have any hydrogen or iodine gases. And then the changed amount, 30% of HI dissociated. So changed amount will be, if we simplify this, we get 1.86 moles. And then the ratio is 2:1:1. Therefore, half of this and that is 0.93 moles will be formed. So at equilibrium, the equilibrium amount will be 6.2 minus 1.86, and we get the answer 4.34 moles. And here the equilibrium amount will be 0.93 moles, and the equilibrium amount of I2 gas will also be 0.93 moles. Now we have to find the equilibrium concentration. So equilibrium concentration, for this we have to divide the number of moles by the volume. So this should be 4.34 divided by 5. Here it should be 0.93 divided by 5, and here also it should be the same, 0.93 divided by 5. Then we get moles per decimeter cube as the unit. And if we simplify this, we get the answer 0.868 moles per decimeter cube. Here it is 0.186 moles per decimeter cube, and here it is also the same, 0.186 moles per decimeter cube. Now we have to find the Kc value. For that we have to write the Kc expression. Kc is equal to H2 gas concentration to the power 1 times I2 gas concentration to the power 1 divided by Hi gas concentration to the power 2, because the stoichiometric value in front of Hi is 2. Therefore, if we substitute these values, should be 0.186 times 0.186 divided by 0.868 to the power 2, and then the units will be in the numerator we have 1 plus 2, 1 plus 1, minus 2. So this will be 0. Therefore, we don't have any units for this Kc expression. And if we simplify this value, we get 45.91 into 10 to the power minus 3. Now let's move on to the next question. Question number 3. Here, 0.8 moles of PCl5 was placed in a vessel and heated to 175 degrees Celsius. When equilibrium has been reached, it was found out that the total pressure was 2 atm and that 40% of PCl has been dissociated. Calculate the Kp value of the equilibrium. Let's write the chemical equation. PCl5 gas will dissociate into PCl3 gas plus Cl2 gas. The initial amount, we have 0.8 moles of PCl5. We don't have any PCl3 or Cl2 gases. And then the changed amount, they say that 40% of PCl5 was dissociated. So 0.8 into 40%, we get 0.32 moles, and the ratio between PCl5 and PCl3 is 1:1, and also between PCl5 and Cl2 gas, it is also 1:1. Therefore, here should be 0.32, and here also it should be 0.32 moles. And then at equilibrium, the equilibrium amount, (0.80 minus 0.32) 0.48. And here the equilibrium amount is the same as the changed amount, that is 0.32. And here also it is 0.32 moles. And we have to find the Kp value. So for this we have to find the partial pressures. Partial pressure of PCl5 is equal to number of moles of PCl5 divided by the total number of moles times the total pressure. So if you calculate the total number of moles, you should get the addition of 0.48 plus 0.32 plus 0.32, and we get the answer 1.12 moles. So the partial pressure of PCl5 will be 0.48 divided by 1.12 times. They have given the total pressure as 2 atm. So if we simplify this, we get 0.857 atm. Now let's find the partial pressure of PCl3, and here should be N PCl3 divided by N total times P total. Then the number of moles of PCl5 will be 0.32 divided by 1.12 times 2 atm. Therefore, if you simplify this, we get 0.571 atm. Since the ratio between PCl3 and Cl2 gas is 1:1, the partial pressures are equal. Therefore, PCl2, partial pressure of Cl2 gas is equal to partial pressure of PCl3, and that is equal to 0.571 atm. Now we can find the value of the Kp of this equation. This should be partial pressure of Cl2 and partial pressure of PCl3 divided by the partial pressure of PCl5. And if we simplify this, we get 0.51 squared divided by 0.857 power 1, and the answer is 0.380 atm. Now let's move on to the next question, question number 4. Nitrogen dioxide analysis to dinitrogen tetroxide. Calculate the value of Kc given that the gas phase equilibrium constant Kp for the reaction is 1.3 times 10 to the power. So for this we can use the equation Kp is equal to Kc times RT delta N. Here, if we calculate the delta N value, it is 1 minus 2, so the answer will be minus 1. Now they have given the Kp value, so that is 1.3 times 10 to the power 3, and we have to find the Kc value, and this should be 8.314 times 273 to the power minus 1. So if you simplify this, we get Kc is equal to 1.3 into 10 to the power 3 times 8.314 times 273. And the answer will be, here the answer will be 2.95 into 10 to the power 6. And the units will be moles cubic meter to the power minus 1.